Recording, all right. All right, guys, again, I'm going to try to record stuff for Storm and see how that goes. To get started, would you grab a calculator? You're going to need one. Let's try this. Mass and acceleration have what kind of relationship? Inverse, which means if one variable goes up, the other goes down. Good. See if you can fill these two numbers out. One of you might need a calculator for, the other one you shouldn't, but if you have to, okay. Oh, something that better be cool, but no, you hit it.
That's 70 at the bottom.
Yes. Hey, look at this, Cedar Point money. Anybody else? Going slowly. All right.
How many people do we have?
14.
Out of, how many do we need?
108. Actually, two things. Whenever everybody's investing in cash, I want to see that I wrote that down.
Okay.
If I can get t-shirts, what size do you want? Okay. Thanks. Oops. So be careful. Mass gets smaller, acceleration gets okay, his first time through shouldn't have been that big a deal. The mass got multiplied by 4. So the acceleration gets divided by 4. I don't even need a calculator because 24 divided by 4 is 6. So 2.4 divided by 4 better be 0.6. That's one you don't really need a calculator for. The other one, I don't know, did you take 70 divided by 200 or 200 divided by 70? It doesn't matter. If you take 70 divided by 200, you get 0.35. If you take 200 divided by 70, you get 2.8. Okay. Something like that. Who cares exactly? That's fine. Here's all you need to know. The mass gets smaller. Acceleration gets bigger. So take this 2.4. What could you do with this to make an answer bigger than 2.4? Multiply them together. What could you do with this to get an answer bigger than 2.4? Divide. I don't care which way you do it. I guarantee you that this times this and this divided by this both give you an answer of 6 point. Okay? I don't care which way you do it. Just know you're supposed to get a bigger answer. It doesn't matter which one of these you come up with. Just do the right thing with it. That's all we're asking. Okay? What really frustrates me, to be honest with you on the quiz, is people that put a smaller acceleration. Wait. Less math doesn't make a smaller acceleration. It makes a bigger acceleration. At least go in the right direction. Okay? So take a look at stuff like that. All right. How about a piece of scrap paper? Even the lab just got back, I don't care. A piece of scrap paper real quick if you would. All right, don't rip out a new sheet of paper. And in 7 seconds, can you draw a car? 6, 5, 4, come on, just draw a car. Don't make a nice big wall. Piece of scrap paper right there, draw a car. 3, 2, 1. Good, your car is done, unless you're slow. Come on. All right. Free body diagram. What's a free body diagram again? Oh, that's right. It's a picture of the object with every force exerted on it. But I need to tell you, my car is going at constant speed, and so is yours. So I'll draw a free body diagram with 4 forces on it of a car going at constant speed. Right? So you have 4 forces, 2 vertical and 2 horizontal. Label them well. I don't need numbers because I don't care what the numbers are. Actually, don't put numbers. Let's work on labeling these things maybe rather than putting numbers in. Good. Yeah, which way's your card going? It doesn't matter which way you want. Sure, left or right.
Oh, right.
Okay, because I'm not sure what to call that either. I got have some. Those two we know what they're called. I'm not sure what to call that one exactly. Have some. Because it sounds like that's what you're hesitating. I would too. And you get two for free, don't you? Yeah. Gravitational force, normal force, those are easy, those are the free ones. My car's going to the right. I'm gonna call this F sub, I wasn't sure what to call it. I mean, can you call it F sub E for engine? The problem is we don't normally label these after the object. I didn't call it F sub E for earth. I didn't call it F sub R for road. F sub P for push, or F sub D for drive. I don't have a name for that, that's fine. You do have a name for this one, however, don't you? Yeah, that's a frictional, F sub F. And if I had did a good job, these two should be exactly the same length, and these two should be the same length. Okay? My car is not speeding up, and neither is yours. We know as soon as you say that, all the forces have to be balanced. Okay? Can you amend your picture to make sure your car's slowing down?
Yeah.
Good, go ahead and do so. Just amend your picture slightly, make your car slow down. Good, what did you do? Okay, which arrow?
I'm going to go for frictional force.
Okay, you made it
Larger.
good. Either make this one bigger, or
That
make that one smaller, or both, it doesn't matter. Make sure there's an overabundance of force this way. Make sure, let's not say overabundance, let's make sure we say a net force that way. Yeah, that's what I'm trying to get at. Good. Okay. All right. I want to take a look at this handout a little bit. What I don't know, I'm making, again, a video for Storm and actually for Andy as well. I don't know for sure if they have those handouts, but here's the biggest one I want to take a look at. Now this thing was stapled weirdly. Okay. One of the sections in this thing, they were trying to get you to look at a bunch of skateboard kind of things. And what they were, the whole point of this whole section was, can you use the idea that acceleration is nothing more than a ratio of force to mass. That's all they're trying to get you to do. And they asked you 8 questions in a row about that, so hopefully you got pretty good at it. Example, here's an example. This is a 1 kilogram cart, and it's a 2 kilogram cart. And they gave you the numbers up there. They said they pulled on this one with 1 Newton of force, and this one with 1 Newton of force. If all I did was look at these numbers, the 1 Newtons, I would say, well gosh, that must be a tie. You pulled on them with the same amount of force, same reaction, right? Oh, wait. Oh, not only does the force matter, the mass matters. And if this has more mass, but you pull on them the same, then shouldn't this one have a bigger acceleration? That's all they were asking you. 8 times in a row. That's what they're asking for. And then it got a little bit more difficult. Right? Because they started giving you pictures like this of things hanging over the side pulley saw. And this will definitely be on your quiz. I guarantee you. I've already written the quiz. And it looks like this. The key is, the cart has a mass of 1 kilogram, and this thing it's hanging here has a mass of 1 kilogram as well. Okay? So, question is, what's the acceleration? Well, acceleration equals net force divided by mass. Use that over and over and over again. And because of that, I would have expected the test to see this. Acceleration equals net force divided by mass. Well, this is the thing that's providing the net force. This is the thing that's doing the pulling for you. And a 1 kilogram object weighs 10 newtons. Hey, how did I know that? 1 kilogram times 10 is 10. That's how I did that, okay? So the net force must be 10. Mass. How much mass? 2. Oh, this thing's accelerating. No, that thing's accelerating. Oh, wait, they're tied together by a string. Aren't they both accelerating? So the total mass is not 1, it's 2. Can you put a 2 in there, and we all know that 10 divided by 2 is 5 meters per second per second. Here's the other way of doing this. If you look at it this way, half the group is doing the pulling, and the other half of the group is just sitting there being inertiaful. That's not a word, I know, but pretend. Does that make sense that if half of the group's pulling, and the other half of the group's just sitting there, you only got half of the normal acceleration of free fall? It's not a fluke, right? That's why they come out to be that way. So then they ask you to go with one more well, and then they did about 8 more in a row, didn't they? So hopefully they went well. So they gave you another example down here, where two objects are holding down here now. So 1 kilogram here, 1 kilogram there, and 1 kilogram up there. Acceleration equals net force divided by mass. How much force is this thing exerting? 10 newtons. How much force is this thing exerting? 10 newtons. Total of 20 newtons. That's why there's a 20 over here. 20 divided by mass of 3, right? This accelerates, and that accelerates, and that accelerates. And that's why they put in 20 divided by 3. And they had you do about 8 examples of that as well. So hopefully that went well. Hopefully that goes well on the quiz, which by the way is not until Tuesday. All right, last couple things to look at. Is this picture has given us trouble in the past. Here we go. It's a picture, and they tell you that the box is moving at constant speed. I'm sorry, no, they tell you it's not moving. They tell you it's not moving, sorry. They say the guy pulls, but it still doesn't move yet. The typical mistake that people make is go, oh, well if it's not moving, well friction must be bigger than his pull. That's not true. If it's not moving, automatically what's true about the forces? They're balanced. In fact, if I drew a picture like this, what would this box have to do? Yeah, accelerate that way. Wouldn't that be really weird if you pulled on something and it shot that way? That doesn't happen. So be careful. These are equal to each other. Lots of people tell me the friction force must be bigger because it's not moving. Wait, not moving is a constant speed. Constant speed requires continuous forces. So the forces are exactly the same. Be careful with that. All right. How about we take a look at the kind of things we're going to do in the lab today, which involves people on a skateboard. Initially, I wanted them to sit. But we had pretty good luck with people even standing on the skateboards last hour. So if you want to stand on a skateboard, that's fine. Okay? Here's the idea. Typical mass for people in this class is 60 kilograms. That's about 135 pounds. So that would be average. It's close, okay? Don't take this mass. You're going to have to measure your own mass. That tells you how to do this. So that's just an example. Typically, friction force is about 15 newtons. But don't take 15 newtons, okay? I'll show you how to measure here in a little bit. Here's my question. If we pull with 85 newtons of force, what is the acceleration of the person? Take a minute and probably a calculator and figure that out. You have an equation for acceleration, right? Great idea. Great idea. You don't need a calculator for that. Alright.
So, yes. Take that divided by 60 kilograms.
That's it. So it's-
Oh, no.
That's it. Don't make it harder than that. Net force, how much? In your head, my suggestion, oh, leftover force. Well, 85 minus 15 leaves 70. That is the net force. So 70 divided by 60 is 1.16, something like that. Yeah, whatever. Okay. That's the easy part. All right. Here's the crux of the lab today. Crux meaning main idea. Let's turn it around. I want the acceleration to be 0.7. My question to you is, how hard do you have to pull to get that to happen?
Well, I'll tell you how hard.
Keep it to yourself. Okay. Same idea, but turn it around. This kind of thing I guarantee you is on the quiz as well.
Gotcha.
see. What's your plan, what is it?
Right there.
Wait,
My
what's
answer
your-
would be that.
That's
Close.
that one works. Right idea, that one.
Oh, sorry, I get it.
Wait, what's your plan? No, no, hold on. Okay, close enough.
Oh, I know what it is.
Yeah, 57.
Yes, so then you're gonna take 42 and you're gonna add it to 50. Yeah. Right? You add 42.
Well, the leftover force is 42.
Minus
Right?
15.
42 plus 15. Yeah. Okay, it's right idea, just be careful. This is the equation. If you solve this, you're gonna find out, well, I need 42 newtons of force. Don't say net force, most people don't know what that means, leftover force. But friction is gonna steal 15 of whatever I do, so shouldn't you overdo it by 15? Most of you finally got that basic idea, so yeah, add 15 to that, we should probably pull with a force of 57 newtons. Okay? Well, that is the idea behind the lab. There's only one more thing I need to show you to make sure that you're successful in the lab. And that is, don't use 15 newtons as a frictional force. I doubt yours is gonna be 15. How do you do this? I'll say this 3 times in a row, and then I won't answer this question during the lab, okay? I got tired of answering it first hour, we did it 3 times. If you get them moving at constant speed, just constant, and you pull with 12 newtons of force, what's the frictional force? That's all you do. If you get them moving at constant speed, right? And then you pull with a force of 17 newtons, guess what the frictional force is? So I don't have to give it, don't use 15, that's just an example, okay? Here's what first hour did. Oh, I think he said, pull them till they just start moving and take that force. No. Last time, get them moving at constant speed. I don't even care what it is. Get them moving at constant speed. And if your pull force says 23, guess what the frictional force is?
23.
That's how you find the frictional force. I'm not going to do that again out in the lab. Okay, we've done it 3 times now, so be careful with that. Other than that, you already have the lab. It's on the second half of the sheet from yesterday. Don't go anywhere yet. I'm going to turn this